Hello students, in today's lecture we are going to derive thin lens equation and to study how refraction occurs in thin lenses. So we now apply the preceding method to discover the thin lens equation. As you can see in the figure, two refractions at spherical surfaces are involved. The simplification we are going to make is to neglect the thickness of the lens in comparison with the object distance and the image distance, an approximation that is justified in most practical situations. Here in this figure you can see that an object is placed at a distance s1 from the lens and its image is formed here at a distance s2 from the lens. Here this is the thickness of the lens. To the left and right of the lens, the medium, the refractive index of the medium is n1, while the refractive index of the lens is n2. So at the first refracting surface, whose radius is r1, the refraction equation from the spherical surface for the first spherical surface is given by this equation, which is n1 upon s1 plus n2 upon s1 prime equals to n2 minus n1 upon r1. While for the second surface of radius r2, the refraction equation is n2 upon s2 plus n1 upon s2 prime equals to n1 minus n2 over r2. Here in the first equation, s1 is the object distance for the first spherical surface and s1 prime is the image formed by the first reflecting surface, while in the second equation s2 is the object distance for the second curved surface, while s2 prime is the final image or the image found by the second surface. And of course I told you that we have assumed that the lens faces the same medium of refractive index n1 on both sides. Now as you can see from the figure, the second object distance means for this second curved surface, the object distance, which is s2, this is the object distance because due to the first refraction from this surface, its image is formed here. This is the first image at this distance and it serves as an object for the second surface. So the final image is formed at this distance here. So this distance, which is given from here to this one, this is the final this is the first image from this first curved surface, and it acts as an object distance for the second surface, and this is the image distance for this second curved surface. So this distance, as you can see, that it is related to the object distance, the second object distance, as s1 t minus s1 prime, because as you can see here, this s1 prime equals to t plus s2. So s2 will be equal to t minus s1 prime, which is given by equation number 3rd, and t is the thickness of the lens. Notice that this relationship produces the correct sign of s2. So if we neglect for the thin lens situation, in the thin lens approximation, if we neglect the thickness of the lens, so equation 3 would become S2 equals to minus S1 prime. So by putting this value of S2 from equation number 4 in equation number 2, we get minus N2 upon S1 prime, because this value, this S1 prime, is S2. Instead of S2, I have put it minus S1 prime. So this term becomes negative, and instead of S2, this S1 prime is brought here. Plus N1 upon S2 prime equals to N1 minus N2 upon R2. And when this equation 5 is added with the equation number 1, so these two terms, minus N2 upon S1 prime, and in equation number 1 the term is plus N2 upon S1 prime, they cancels out, and we are left with N1 upon S1 plus N1 upon S2 prime equals to N2 minus N1 into 1 over R1 minus 1 over R2. Now, as from the figure we know that S1 is this S1 is the original object distance, and S2 prime is the final image distance. So we can now draw their subscripts, and we can write them, the equation as 1 over S plus 1 over S prime equals to N2 minus N1 upon N1 into 1 over R1 minus 1 over R2. I have just removed the subscripts here. Here this S is the object distance with respect to the lens, and this is the image distance with respect to the lens, and this N1 from these two terms is brought to the other side in the denominator. You can see it. So also we know that the 1 over S plus 1 over S prime is equal to 1 over F. So I have just replaced these terms by 1 over F. So this is the lens equation. From lens equation I have put it 1 over F instead of these two terms, and the remaining equation is as it was before. So this equation 7, sorry, I have write it here equation number 28, but it is equation number 7. This equation number 7 is called the lens maker equation, because it predicts the focal length of a lens fabricated with a given refractive index and radii of curvature and used in a medium of refractive index N1. So if we know the radii of the faces of the lens, and we know the refractive index of the lens and the medium surrounding the lens, we can compute the focal length of the lens. So the wavefront analysis for the plane wavefronts, as you can see in the figure, it indicates that a lens which is thicker in the middle, it causes convergence, and the one which is thinner at the middle causes divergence of the incident parallel rays. So the portion of the wavefront that must pass through the thicker region is delayed relative to the other portion, as you can see here, because in the lens which is thicker, in the lens convex lens, as you can see that when this plane wavefront is passing through this lens, so it at the middle region it travels more distance as compared to its edges. So here the wavefront is slowed down more as compared to its edges. So this at this portion the wavefront passes more rapidly than the portion which is at the middle, so it causes to delay the wavefront at the middle, so it converges the the parallel beam of light or the parallel wavefronts, plane wavefronts into a converging rays of light. Similarly, in case of concave lenses, which is thinner at the middle and thicker at the edges, plane wavefronts are diverges because at the middle region it passes more rapidly as compared to the edges of the lens. So the wavefronts diverges. Simple ray diagrams for converging or convex and diverging, or which is called concave lenses, are shown in these two figures. The thin lenses are best represented for the purpose of ray construction by a vertical lines with edges suggesting the general shape of the lens. Ordinary arrowheads for converging lenses, inward arrowheads for diverging lenses. So as you can see that this is a thin lens which is represented by an arrow, and it is denoted with ordinary arrowhead. So a line with ordinary arrowheads will represent a convex lens, while a line with inverted arrowheads will represent a concave lens. So the graphical method of locating images with respect to with spherical mirrors, which we discussed earlier, make use of the three key rays. This procedure is outlined in these given figures. So it makes use of three key rays. This procedure is outlined in the given figures. The three rays leaving the tip of the object changes direction due to refraction at the thin lenses interfaces. And so here you can see in both the situations, for the convex and for the concave lenses, an object is placed at some distance from the lens and three rays are leaving the head of the tip of the object and are approaching towards the lens. As you can see in these figures, they are represented by 1, 2, 3 rays. So when the ray first, as you can see that it is a ray which is leaving the tip of the object parallel to the optical axis and undergoing refraction at the lens surface and passing through the right focal point F of a converging lens, are as given in the figure A. Here you can see that the first ray, it is parallel to the optical axis, and when it passes through the convex lens it will pass through the focus point, as you can see at this point. While in case of concave lens, when a parallel ray of light is parallel to the optical axis is passed through the concave lens, it will diverge and it will appear to start from the first focus point. The ray second, which is a ray leaving the tip of the object and passing through the left focal point, as you can see here, is passed through the convex lens, and when it is passed through it, it will go parallel to the optical axis. While in case of concave lens, when a ray which is initially going in the direction of the right focus point, as you can see that it is traveling in this direction, which is traveling towards the right focus point, when it passes through a concave lens, after passing through the concave lens it will go parallel to the optical axis, while the third ray in both the situation, when it is uh, passed through the optical center of the convex or concave lens, it will go straight. There will be no refraction. In constructing ray diagrams, as you can see in these two figures, we observe that except for the central ray, the third one, each ray refracted by a convex lens bends toward the axis, and each ray refracted by a concave lens bends away from the axis, as you can see in both the figures, except for the third ray. So the convex lens causes convergence while the concave lens causes divergence. From either diagram, the angles subtended by the object and image at the center of the lens are seen to be equal, as you can see from these two figures. Here at the center of the object and the image, in each case, when for this first ray or second ray or the third ray, the central angles are equal, like in this situation, or for the second ray you can see these two angles, and similarly for the third ray. So for either the real image or the virtual image, because the first case, in the first figure, the image is real, while in the second figure the image is virtual. So in both situations it follows that the ratios of their tangents of the angles, as you can see in these two situations, the tangent of these two angles are given by this expression, which is h0 over s, where h0 is the height of the object and s is the distance of the object with respect to the lens. This is equal to hi over s prime. Hi is the height of the image and s prime is the distance of the image with respect to the lens. So these two ratios will be equal, and the lateral magnification is defined as absolute of m equals to absolute of hi over h0, which is equal to s prime over s. So in accordance with the sign convention adopted here, the magnification should be negative of the ratio of the image and object distances. So whenever we are going to find the lateral magnification, so that will be the negative of the image distance, the ratio of the image distance to the object distance, as you can see from equation number 8. So there are two situations when object distance is also positive, means for the when object is real and also the image is real. When s is positive and s prime is positive, then m will be negative, because in that situation image is inverted, as you can see in this figure. This is object distance and this one is image distance, and both are positive, while m will be negative, because here you can see that the image is inverted. While in the second situation, when object distance is positive, means object is real, and the image distance is negative, this means that the image is virtual, then m will be positive. This means that the image will be upright, as you can see in this figure. Here this distance is the object distance from here to here. This is the object distance, which is positive, and this distance is negative, which is because it is to the left of the lens. So s prime is negative here, and the magnification will be positive here. So by positive we mean the image is upright, as you can see here in this figure. So I hope you have understand this lecture. Thank you very much.